All right, this is APBC Calculus. We're doing Unit 9, Section 8. This is a BC only topic. We are finding the area of a polar region or the area bounded by a single polar curve. All right, so we'll also talk polar arc length while we're here. All right, so the area bound by a polar curve, so you can see here that I've got a chunk of a curve I called r comma theta, or r of theta rather. Um, and I'm going from theta is some alpha to theta is some beta, right? The area is 1/2 the integral from alpha to beta of r squared d theta. So you definitely want to memorize this. Like, this is a non-negotiable. It's going to show up on your AP. There's no excuse for not memorizing this. Make a note card if you need to. Please remember it. For me personally, my hangup was always the annoying 1/2. So we'll walk through why there's a 1/2 in the next slide. You can definitely ignore that if like you don't have to pay attention to how I'm going to get this formula if you don't want. But again, just to point out that this is definitely a formula you want to memorize, put this on your really important, it's going to show up on my exam, I have to memorize it list. All right, so why is there a 1/2? Why is the radius squared? If you don't care, please feel free to skip the next short section of this video. That's fine. I don't care. Just memorize the formula. If you do care, then I'm going to walk you through why. So let's look at the area of a sector of a circle. So here's a circle. A sector of a circle is like a slice of the pizza, right? It's a central angle of theta. So this is the center of the circle, right? If I wanted the area of the sector, which I denoted as A sub s, it would be whatever fraction of the circle pi is out of. So this is what fraction of the circle we're talking about, right? Because 2 pi would be the whole circle, so theta over 2 pi is what fraction we're talking about. And then this is the total area of the circle. So it's the fraction of the circle that you're looking at, like half the circle, a third of the circle, 1/5 of the circle, times the area of the circle. If I clean this up, I get a theta over 2 times r squared, or a 1/2 r squared theta. But in calculus, theta is not a big angle. Theta is a tiny slice, like an infinitely small slice. So instead of using theta, we use d theta to mean an infinitely tiny slice. So since it's not a circle, the radius isn't just r. The radius is some r in terms of theta because, again, calculus, it's not just a circle. The radius will vary. So if we replace this theta with a d theta, right, and we replace this r with an r of theta because it is not a constant function, we get that this tiny slice of area, which I'm going to call dA because it's the area of the tiniest little slice of the circle, infinitesimally small, is going to simplify to be a 1/2 r of theta squared d theta. Well, if I want the area of the entire thing, I'm going to add up all the tiny little slices, which we call integration, and then there's your formula with the 1/2 r squared of theta. And that's it. So let's go ahead and walk through this. We're going to use a calculator to find the area bound by the polar curve in this given window, right? So that's my window, right? I'm starting at an angle of 0. I'm going to an angle of 2 pi over 3. And my job is really 100% just to write the formula that I have memorized. This area, right, should be 1/2 the integral from 0 to 2 pi over 3 of r of theta, which is this thing, quantity squared with respect to theta. This is the part that is my job, and then the rest is my calculator's job. Now, I don't care if you're in polar or if you're in parametric, or if you're in function, right? I am going to make the argument that function mode is the most versatile of all the options. So I'm usually going to stay in function mode, and I'm usually going to just use y and x instead. It's up to you. You can definitely be in polar mode. There are times that it is useful to be in polar mode, but for me personally, I find that I get more functionality out of using function mode. So I'm going to quit out of this. I want math 9, right? So 0.5, math 9, right? And what I want to integrate is the thing I called y1 squared, right, comma, with respect to x, because that was my theta, from 0 to 2 pi over 3. I'm going to show you in a sec that this works the same way if I do it in polar mode, just so that you believe me, and it really doesn't matter. So that's my answer, right? Now, if I go to mode and I go to polar, I just want to show you that it does work the same way. So if I go to polar, your calculator doesn't actually care what variable is standing in for what, as long as you understand how it works. Like, as long as you're using the correct, you're not mixing and matching your variables, right? So cosine of 2 theta. If I quit out of this, I could still do math 9 the same way I've been doing, right? So I could do math 9, right? and I want to, oh, sorry, I forgot my 1/2, second insert 0.5. So I want to go to variables, I go to y-vars, and this time I'm going to pick polar, and I want r1 squared, comma, with respect to theta from 0 to 2 pi over 3. Same thing, same answer. Doesn't matter which way you do it. So just drag this over here. So same thing, same answer, doesn't matter which way you do it, right? You can be in polar, you can be in function, you could be in parametric. It'd be weird, but you could. Okay, so same thing here, right? Your job is fundamentally to write the integral and then type. So here's my pi over 6, right? And this is my pi over 2, right? This is the area we're talking about. So my job, or rather in this case your job, is to write 1/2 the integral from pi over 6 to pi over 2 of r quantity squared with respect to theta. So this part is you. You have to do that, right? And then you have to type it in your calculator, right? So it doesn't matter. I'm already in polar, so I'll stay in polar. Sometimes I just use the path of least resistance if I don't need anything special out of my calculator, right? And then I'm just going to hit second enter, and I'm going to change the bounds because I already changed the r value. Oh, my bad. Second pi over 6, comma, pi over 2, and then double check that everybody's right. Yep. And so I get that this is approximately a 0.996. And that's it, right? So this is you, and this is your calculator. That's the amount of work that you're going to have to show on this. You have to communicate the understanding by setting up the correct integral, and then type, and that's your whole job. All right. Let's keep moving. All right, so sometimes you're going to be asked to find the area enclosed, sometimes you'll be asked for the area enclosed in a curve, but you'll be given no bounds. If that happens, you usually need to find the bounds. So you'll need to find where r is 0 because that's when these things touch again at the pole, okay? It's like when a loop closes. So find the bounds for one loop of the polar curve. There are multiple correct answers here, and then we're going to set up but not integrate an integral expression for one loop, for the area of one loop. So to find the bounds, right? So to find the bounds, what I need to do is I need to set r equal to 0. So 0 equals sine of 2 theta. There are two ways to do this. So option 1 is to say, oh, the 0 is the y on the unit circle. That happens at these spots here, right? So essentially my 2 theta is going to be plus or minus 0, pi, 2 pi, 3 pi, et cetera, So my theta is plus or minus 0, pi over 2, pi, etc., right? Like 3 pi over 2, etc., right? So blah, 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 2 pi, okay. And if you see that, right, I'm going to pick, so I say, oh, you know what? I'm just going to do this loop. This loop seems to start at 0 and end at pi over 2, which jives with what I'm seeing here because those are two of the bounds, right? So that would be this loop. I pick, so for my bounds, I pick theta equals 0 to theta equals pi over 2. And I could have picked any two consecutive ones, essentially, right? I could have picked negative pi over 2 to 0, and that would have been this one, or I could have picked pi over 2 to pi if I wanted this one, right? And so then the area I'm going to set up for one loop, right, is going to be 1/2 the integral from the bounds I picked of my r, which is sine of 2 theta, quantity squared d theta. And I was told to set up but not integrate, and that is it, right? So one thing to mention here is I did mention that there were two options right here. The other option is to recognize that there's a trig identity that says this is 2 sine theta cosine theta. And then you could literally find when sine is 0, which is at all the pi's, right? So 0 and pi and 2 pi, etc., right? Dot, dot, dot. And you could find when cosine is 0, which is at all the pi over 2's. So you'd get the same answer, right? Pi over 2, 3 pi over 2, etc. Again, you'd get the same answer. Either way, you get the same bounds. All right, same thing here. You've got this cosine of 3 theta. I want you to find the bounds of one loop, right? There are multiple correct answers, and then set up but do not integrate an integral expression for the area of that one loop, right? So first thing you have to do is find the bounds, right? So you're going to say 0 equals cosine of 3 theta. So that's where 0 is x on the unit circle, right? So that's going to happen here and here at all the pi over 2's, right? So my 3 theta is going to be plus or minus, because in this situation, this would be a positive pi over 2, but it's a negative pi over 2, etc. So pi over 2 and 3 pi over 2 and 5 pi, all the odd pi over 2s, 5 pi over 2, 7 pi over 2, etc. Right, all of those. So I'm going to get that my theta is a pi over 6 and a 3 pi over 6, which we'll clean up in a sec, and 5 pi over 6, 7 pi over 6, etc. Okay. So there's two ways to do this, right? So if you look at this one's actually negative pi over 6 to pi over 6. You can't call that 11 pi over 6 because you have to be integrating in order, right? If you wanted the next pair, right? So you can sort of find these by finding what each angle that sort of flanks it is, right? So this one here, right? This is actually a pi over 2, right? So this would be pi over 2, right? And then this guy right here is 5 pi over 6. So you could find that, like you could say, oh look, that's these two being consecutive, right? So you could find that one. I don't care which one you pick. I'm actually going to pick this one, but it doesn't matter which one you pick. So in this case, I pick theta is negative pi over 6 to theta is pi over 6, but you could have picked other options. I just thought this one was the nicest one, and you can see that it's around 0, right, because this is the line where theta is 0, so that's why I ended up with a positive and negative part of that angle. And so then my area of that one loop would be 1/2 the integral from negative pi over 6 to pi over 6 of cosine of 3 theta quantity squared with respect to theta, and that's it. Again, there's infinite correct answers there. I picked one of them. All right, recall that the average value of any function on the window from a to b is given by 1 over b minus a times the integral of f of x dx. So also recall that r of theta is just directed distance from the pole. So if you're asked to find the average distance from the pole or the origin or whatever, right, the average distance from the pole, they're just asking you to use this average value formula, but instead of using f of x, you're using r of theta, and that's the whole deal. So it's the same formula. You're just using r of theta instead of f of x. You're using d theta instead of dx, and you're using beta and alpha instead of a and b. All right, so let's go ahead and do a calculator. What is the average distance from the origin of the point on this curve? Okay, so what we're being asked to do, right, this is going to be, so the average distance is going to be 1 over b minus a times the integral from a to b of the r function with respect to theta. This part is the part that I have to do. I don't have to make it nicer than that, and then I use my calculator to find a value, because that's how these calculator questions work. You have to communicate the correct math notation, and then you can use your calculator to find a value. I don't care if you're in function mode or if you're in parametric mode. It really doesn't, or sorry, if you're in polar mode. Wouldn't really make sense to be in parametric here, but I don't care which mode you're in. You just have to be right, okay? So you can integrate correctly in either mode. I happen to be in polar mode right now, so I'm just going to do polar because it's easier. So there's my r. So I would suggest that maybe it's easier for you to simplify this. You don't have to, but you might have an easier time recognizing that this is a 1 over pi over 2, which is a 2 over pi. So I'm probably going to do that for my own benefit. Most of our simplifying at this stage of math is selfishly for our own benefit. So 2 over pi, right? Times the integral, so that's math 9, of the thing I called R1. So I go to polar and I want R1, comma, with respect to theta from 0 to pi over 2. And there's my answer. So I get that it's this. And again, you're not writing all the calc notation that you typed, like you're not writing what you type, but I'm writing it here because I need you to understand how to type stuff, right? That's important. All right, same idea here. You give this one a try. I want the average distance, right? So that average distance from the curve is going to be 1 over pi over 3 minus 0, the integral from 0 to pi over 3 of my r function with respect to theta, right? So this is the part that you have to write, and then the rest is on your calculator. Right? So you have to write it, and then you have to type it. So I'm going to be pretty lazy, and I'm just going to retype over what I already have in my R1 because that's just easier. Okay, so that looks right. And then I'm going to quit out and I'm going to second enter, and then I can just change. Instead of being a 2 over pi, this is now going to be a 3 over pi, right? Because this piece right here is actually a 1 over a pi over 3, which is a 3 over pi, right? So I'm going to go ahead and change that to a 3, right? And then I need to change the bounds. So the bounds were 0 to pi over 3, and I think that's the only change because I used R1. So I get that this is a 1.061 or 2, depending if you round to truncate, right? Moving on. Okay, so let's talk polar arc length. You can find polar arc length the same basic way you find parametric arc length. The only difference is that it's a theta instead of a t. So I'm not going to go into a ton of length about this. It's exactly the same formula. It's a theta instead of a t. The only thing you have to be cautious about is remember that x is r cosine theta and y is r sine theta, which makes things a little more difficult. But let's go from there. All right, so set up but do not integrate an integral expression for the arc length of the polar curve. So set up but do not integrate means it doesn't have to be pretty. You just have to carefully make sure that it has every piece it needs. You don't simplify a lot. So first thing I need is I need x of theta. Well, that's going to be r, so 2 theta, cosine theta. And my y of theta is going to be r sine theta, right? And then I need x prime of theta. Well, that's going to be a product rule, right? U and v. So u dv plus v du. My y prime of theta is going to be u dv plus v du. And you can clean that up if you want. I mean, there's not a huge incentive to do that, right? So my my arc length is going to be the integral from 0 to pi over 3 of the square root of, and then this is kind of a lot, but we're going to make it work, right? This thing squared, so that's a negative 2 theta sine of theta plus 2 cosine theta squared, right? That's my, that's x prime of theta. That whole thing is x prime of theta, right? And then squared, plus 2 theta cosine theta plus 2 sine theta, whole quantity squared, and again, that whole thing in here is y prime of theta. You don't have to write that, I'm just clarifying it for you. And that's my job, set up but don't integrate. So there's, so let's make that a different color. So here's my answer, right? So my job is to know the formula. I was not asked to integrate it. I do need to find x prime of theta and y prime of theta. All right. Last one, you're going to try the same thing. So again, you're going to need x of theta is a theta squared cosine theta. Y of theta is a theta squared sine theta. You're going to need your x prime of theta, right? So that's going to be u dv plus v du, which, you know, you can clean up however you want if you need to clean it up a little, right? And then my y prime of theta is going to be u dv plus v du. So that's a theta squared cosine theta plus 2 theta sine theta. And again, I'm not actually integrating, right? I'm just setting it up. So my arc length, and I do communicate really clearly, hey, this is the thing I'm talking about, here's my answer, this is my arc length, is the integral from 0 to pi over 2 of the square root of the thing I called x prime, so that's negative theta squared sine theta plus 2 theta, oh, sorry, whew, be careful, when I cleaned that up, I was wrong. 2 theta cosine theta, that's where you got to be careful, squared, plus this thing, right, which was theta squared cosine of theta plus 2 theta sine theta, quantity squared with respect to theta. And I ran a little bit out of room, but that's the idea. So that's my answer. And again, be really careful because it's easy to just accidentally miscopy something. Like right here, that was a cosine and I accidentally made it a sine. All right, that's it for this video.